So this is week 3 of thermodynamics course. So previous week we looked at um, first got to know of the terminologies used in thermodynamics. We saw what is process, what is state, and then next week we looked at what is work and heat. How do we calculate for a process, calculate work, and how the work is distributed across the systems, and so on. So this week we'll continue some problems on similar work done, and uh, proceeding with the first law of thermodynamics. To start with, I'll just give you a brief on the first law of thermodynamics.
வந்துட்டான் தெர்மோடைனமிக்ஸ் லைவ் ப்ரோக்ராம்
So first law of thermodynamics. So it's basically zeroth law says your temperature are in equilibrium when multiple bodies are in contact. You have equilibrium. So that's what thermal equilibrium is defined by zeroth law of thermodynamics. The first law says that you have energy is constant. So that's the simplest form of understanding first law of thermodynamics. So for across a cycle, or you design a cycle with multiple processes. So when you go through the cycle, what you find is the net heat which is supplied to by the cycle, and it will be equal to the net work done. So basically your internal energy will be zero. That is your property, so it will be zero. So integral of that will be zero. So Q net is W net, and that was found by Joule. And you later, for a process, you write your net change in internal energy across two states is equals to Q minus W. So that is your first law. And the other parts is your we'll look at the next week on two phases. So before that, we need to understand pure substance. So pure substance is something which is homogeneous. You see, it doesn't vary. So if you have air, so as air, you have nitrogen, oxygen, and other gases. So you can assume that also can be as a pure substance, because it doesn't vary. The molecular concentrations, they don't vary, and in that will have a single phases. And we next week we'll look at the two phases. So this week we'll look at only with the single phase problems. So moving on. So first question for today is carbon monoxide gas contained within a piston cylinder assembly undergoes three processes in series. So process 1 to 2 is a constant pressure expansion at 5 bar from V1 is 0.2 meter cube to V2 is 1 meter cube. Then you have process 2 to 3, so that which is a constant volume process. So it is now going from 5 bar and 0.2 meter cube, 1 meter cube to pressure of 1 bar. Then you have process 3 to 1, which is compression from state 3 to the initial state 1. So that you follow along PV equals to constant line. So that is also an isothermal process. Okay. Check the process in series on PV coordinates and evaluate the work for each process in kilojoule. So if you plot it in PV, this is how the process will look. So 1 to 2 is a constant pressure process, so you have a horizontal line, and then it's a constant volume, so vertical line here, and then PV equals to constant. It's kind of, it's in a hyperbola kind of. So 1 to 3 you connect those. So this forms a cycle. So now we need to find out evaluate the work for each of the processes. So first one is constant pressure. So we can straight away find out everything will be integration of P dV. So first is pressure is constant, you take it out, you have integral dV, so P delta V. So that will give you the work done for process 1 to 2, and 2 to 3 your volume is constant, so there will be no work generated. So integral P delta V will be 0, and then 1 to 3 you integrate PV equals constant. So you write pressure in terms of volume, constant by volume, and integrate it, then substitute it back. You will get it in terms of natural logarithmic term. So this is how it will look. So for process 1 to 2, so constant pressure, integral PdV, you get P1 into V2 minus V1. So we know both the volumes, we know the pressure. So it's a constant pressure at 5 bar, and it's expanding from 0.2 to 1. So it's an expansion process. So you get work. So 5 into 1 minus 0.2 is 400 kilojoules. So since it's positive, that is the net work which is received, or the system, the process is generating. Then process 2 to 3 is a constant volume process, so piston will not move. So in that case, your work done is 0. And then process 3 to 1 is PV equals constant. So integrating, you will get P1 V1 ln V1 by V2. So substituting the volumes and pressure terms, your pressure is 5 bar and volume is 0.2. So you know both the end and final conditions. In that case, you will substitute, you get work done as minus 160.9 kilojoules. So this says that you have to do work. So work is negative here. So the net work is the summation of all three. So summation of all three will come out to be 239.1 kilojoule. So this is the net work which is generated by the cycle. So any doubts in this? The simple process, previously we saw individual process, here it's a combined process with the cycle. Okay. So next question. We have 15 kg of carbon dioxide gas which is fed to a cylinder having a volume of 20 meter cube and initially containing 15 kg of CO2 at a pressure of 10 bar. Later a pinhole develops and the gas slowly leaks from the cylinder. So you have a 15 kg carbon dioxide cylinder and the volume is given is 20 meter cube, and you have 15 kgs at start with a pressure of 10 bar. So that's the scenario, and you have a pinhole which is generating, so your CO2 starts leaking out. So with this case, we need to find out first the specific volume of the CO2 the cylinder initially, then repeat the process if the cylinder after the 15 kg has been added. So initially you have 15 kgs, you are adding 15 kgs, and then there is a pinhole generating. So after adding 15 kgs, what is the specific volume? So that's the second case. Then plot the amount of CO2 that has leaked from the cylinder in kg versus the specific volume of the CO2 remaining in the cylinder. So how do you solve this? So these are the three scenarios. So initially you have a cylinder which is having a volume of 20 meter cube and the mass is of 15 kgs. So in that you are adding again additional 15 kgs of CO2. So now the net kg has become 30, and now there is a pinhole which is generated and the leak starts happening. So each of the cases you need to find out the specific volume and how the specific volume varies with respect to the leak. So we know specific volume is the volume divided by mass. So here the volume remains same, but the mass is decreasing. The initial case you are adding 15 kgs, and then later on because of the leak the mass keeps on reducing. So the specific volume initial case is 20 by 15 kgs, 20 meter cube by 15 kgs. So that gives you 1.33 meter cube per kg. And then when you are adding 15 kgs of CO2 to it, now the net mass which is there inside the cylinder will become 30 kgs. So the specific volume now becomes 20 by 30, so which is equals to 0.67 meter cube per kg. So the simple problem. So the next, when the leak starts developing, so initially the mass is 30 kg now. So amount leaked will be 30 minus the mass in the cylinder, and the mass in the cylinder can be expressed as minus 20 by V. So this is how the equation will look like. So the amount which is leaked in terms of specific volume. So the plot, if you vary V from, they have given to vary till 1 meter cube per kg. So initial volume is 0.67. So from 0.67 it will vary to 1. Because if you see at 15 kgs, your specific volume is 1.33. So you are varying from 0.67 to 1. So this is how the graph will look like. So here the assumption is that when though the leak is generated, you have a uniform specific volume across the cylinder, and the leak is very small, very slow. It's happening very slowly. So that's the assumption which we make for this. Any questions? Okay. Next question is, a certain amount of air is enclosed inside a vertical cylinder by a frictionless leak-proof piston as shown in the figure. The cross-sectional area of the piston is 20 centimeter square. Initially, the pressure of the air in the cylinder is 60 kilopascal. The cylinder is connected through a valve to a rigid vessel which initially contains air at a pressure of 30 kilopascal. The lower face of the piston is exposed to the atmosphere at 100 kilopascal. The valve is now opened and the piston slowly moves a distance of 12 centimeter from its original position. Calculate the work done by each of the following systems: A, the piston; B, the atmosphere; and C, the air. So what we have here is, we have a piston cylinder arrangement, and which is connected to a air reservoir or compressed air tank. So what is happening is, initially the piston is at rest, and you have given the piston cross sectional area and the initial pressure in the cylinder. So which is connected to a air reservoir. So when this is open, the cylinder is connected through a valve to a rigid vessel which initially contains air at a pressure of 30 kilopascal. So the air here is at 60 kilopascal, which is inside the piston is 60, and which is inside the reservoir is 30. So which is all lower than the atmospheric pressure. So what will happen is, atmosphere will try to compress the piston. So it will try to move, push the air inside the reservoir, and it will do so till it reaches an equilibrium. But here they have said that the piston moves to a distance of 12 centimeter from its original position. So the piston is moving by 12 centimeter. So that much amount of volume of air is being pumped inside the reservoir. So in this case, we have to now assume, find out what is the work done for each of the cases: the piston, the atmosphere, and the air. So to start with, we write a force balance for the piston. So the piston, what are the forces acting? One is the atmospheric force, which is acting upwards, and then the pressure inside the piston cylinder, so which is at 60 kilopascal, which is acting on the piston, which is downwards, and then the weight of the piston. So these are the forces which is acting. So we get P atmosphere into A equals P into A plus mass of piston into G. So using this, we can estimate the mass of the piston because initial pressures are known and the atmospheric pressure is known, and we also know the cross-sectional area of the piston. So using that, the mass of piston is A by G into P atmosphere minus P1, which is 100 minus 60 into 20 centimeter square. So 20 into 10 power minus 4 divided by 9.81. So we get 8.155 kgs, kilograms of mass of the piston. Now we need to find out the work done in each of the case. So the piston, whatever work is done by the piston is equal to the change in its potential energy. So you get mg into h, or the upward movement. So that's what the piston is gaining as a work. So whatever work is being done on the piston, it is potential energy is getting raised. So mg into delta h, or z2 minus z1. So here it's negative because the piston is taking, you have to do work on the piston to raise its potential energy. So it is negative. So 8.155 into 9.81 into 0.12, because it's moving off by 12 centimeters. So that gives you minus 9.6 joules. Then the work done by the atmosphere. So the work done by atmosphere is P into delta V, integral P delta V. Your pressure is constant. The atmospheric pressure which is acting on the piston is constant. So your work done by that is P delta V. So P atmosphere into V2 minus V1. So you get 100 into 10 power 3. So you get into the change in volume, which is area into the distance where the piston moved. So which is 12 centimeter. So you get 24 joules. And similarly, the work done by the air is if you see here, the air is also at constant pressure of 60 kilopascal. If you see the force balance here, at any point of time, the piston weight will not change, the atmospheric pressure is not changing, so your P will also remain constant. So the air pressure inside the cylinder is always at 60. So the whatever work which is done by the air is equal now. So your pressure is constant and pressure into delta V. So your work done by air is 60 minus 60 into 10 power 3 into the same change in volume, which you get minus 14.4 joules. So if you sum up all the work, you will get net work is 0 in this case. So that W atmosphere plus W piston plus W air is 0. So you can see, so what happens is this is nothing but the W system plus the W surrounding, that's why it's 0. If you see, W atmosphere is your surrounding, whatever work, and W piston plus W air is the system. So system plus surrounding, the net work is 0 because that becomes an isolated system. Hence this is 0. Any doubt in this question? Okay. Then moving on to next question. Consider a frictionless piston cylinder arrangement shown. Initially, the air contained in cylinder A occupies 0.0864 meter cube and is at 200 kilopascal and 300 Kelvin, while the air in cylinder B occupies 0.0398 meter cube and is at 300 Kelvin. The cross-sectional areas of cylinder A and B are respectively 0.00786 meter square and 0.00393 meter square. Heat is now supplied to cylinder A, causing the piston to move slowly downwards by 2 meter. The total mass of the piston and connecting rod is 10 kg. Cylinder B is completely insulated, and pressure of the air in cylinder B after the process is 442 kilopascal. So this is how the process occurring. So what you have is two piston cylinder arrangement, and you have a common pistons. So both the cylinders pistons are connected through a common shaft. So and initially those two piston cylinder arrangement will be in equilibrium because of the weights of the piston and the pressures are inside each of the cylinders, and the atmospheric pressure all will try to balance it, and uh, the pressure will be such that the piston is not moving, so they are in equilibrium. So in that case, the initial case, they have said that A has some volume which is given and is at 200 kilopascal and 300 Kelvin. So that is given. And similarly, B, you don't know the pressure, but you know what is the volume occupied and the temperature. So this two you know. So initially we need to find out the pressure in cylinder B. So what else is given is the cross sectional area is given, and they have said when heat is supplied to cylinder A, that the piston starts moving down by 2 meters, and at the end your when piston has moved by 2 meters, your cylinder pressure in B is 442 kilopascal. So that is given. So we need to find out mass in cylinder A, initial pressure in cylinder B, mass in cylinder B, then the atmospheric pressure, then the work done by piston, the work done by atmosphere, the work done by piston, then what is the final volume in B, then final temperature in B, and work done in by the cylinder B, the piston B, then also final pressure in A, final temperature in A, heat supplied. So there's a lot of things which have to be found out. Let's look at break it down and look at one by one. So the first one is we need to find out the mass of air in cylinder A. So air, we can assume it to be an ideal gas. So we can use an ideal gas equation. So PV equals mRT. So from there we can find out M. So initially we know pressure, volume and temperature for cylinder A, and for gas air we know R. So substituting the values, we have P is 200 into 10 power 3, and volume is given as 0.0864, and divide by R as 288.68 into 300 is the temperature. So you get the mass is 0.2 kgs, and then at any instant what is the force balance, force acting on the piston. So we write a force balance for the piston piston assembly here. So here if you consider the top portion A,
அவர் என்ன சொன்னாரு, நான் மேம் கிட்ட பேசிட்டு மேம் கிட்ட அனுப்பிச்சுதான் சொன்னாரு. இப்போ பாருங்க நம்ம லாஸ்டா
so the force acting in cylinder piston A is, so the pressure due to the gas inside the cylinder, and then which is acting downwards, and the force due to the atmospheric pressure which is acting upwards. So that is the net, will create a net downward force. So P minus P atmosphere into the area of piston for the cylinder A, plus you have the weight of the piston, and then which is balanced by upward force in the cylinder B. So you have pressure in the cylinder B minus the atmospheric pressure which is acting. So you P minus P atmosphere into area of the cylinder B. So with this we need to find out the next is the initial pressure in cylinder B. So what we know is we know the initial pressure in A. So only thing which we don't know is the initial pressure in piston cylinder B. So the rest all values we know. So we can estimate the initial pressure in cylinder B. So rearranging, this is what we get. So P atmosphere 1 minus area of cylinder A by area of cylinder B plus same area ratio into initial pressure in cylinder A plus mass weight of piston divided by area of piston B. So substituting the values, we know P atmosphere, which is 100 kilopascal. We know the areas of pistons are given here, cross sectional areas, so 78.6 centimeter square and 39.3 centimeter square. So the areas are known, and the weight is also given as 100 kg and G is 10. So substituting here, we can find out the initial pressure in cylinder B is 325.45 kilopascal. Then C is mass of air in cylinder B is similar ideal gas equation. We know now pressure, initial volume and temperature is known. So we have found out the initial pressure. Now using that we can find out the mass, so which comes out to be 0.15 kgs. Next is we need to find out the work for each of the component. So the first is the work done by the atmosphere. So just like the previous example, here also your work done by atmosphere will be same because it exerts a constant pressure. So P atmosphere into delta V. So but in this case it's both the volumes, change in volume of A and change in volume of B. So given that the piston assembly moves down by 2 meter, so what is happening is the area of piston, so the volume of piston A is expanding. So the volume moved is 2 into area of piston A. So here it's negative. Since we are looking it from the atmospheric point of view, this is like atmosphere, you're trying to compress the atmosphere. So that's why it's negative. So the piston is doing work on the atmosphere. So you are getting work input. So work input is negative, work output is what is positive. So that's why it is minus 2 into area of piston A. And or the other way of looking at is V initial minus V final, you get my negative. Then the volume change in piston B is 2 into area of piston B. So because the piston is connected, so if piston A is moving by 2 meter, piston B will also move by 2 meter. But now the piston in cylinder B it is getting compressed. So therefore that atmospheric pressure total will be minus 786 joules. So this is the net work output, if you can see. So the piston work will be again similarly the change in potential energy, so which is minus 200 joules. So the piston, the work done by both the gases, if you consider, how will you find that? So that will be the summation of all the work will be 0. So W atmosphere plus W piston plus W gas will be 0. So W gas will turn out to be 986 joules. So we have found out the atmospheric pressure, work done by atmospheric pressure, and then the piston. Now we need to find out at any instant, consider the what is the F part, final volume in B. So we need to find out the final volume. So the final volume is the total two volumes will remain same because it's connected by say constant piston. So the piston, so if it moves by 2 meter, so initial volume in the cylinder B is known. So now since it has moved by 2 meters, we can estimate the final volume. So V2B is V1B minus 2 times the area of piston. That will give you the volume change. So that comes out to be 0.03194 meter cube. Next is final temperature. So final temperature, the same ideal gas equation. The final pressure is, we have found out. The final pressure is given 442 kilopascal, and then the final volume has been calculated, and we know the mass. The initially what was calculated, because it's a closed system, the mass will not change. So the mass is constant and we know R, so we can estimate the temperature. So substituting the values, V2 is 442.84 and then V2 is 0.03194, which we have calculated, and mass is 0.15 and R is 288.68. So this gives you temperature of cylinder B, or the gas in cylinder B at the final condition is 327 Kelvin. So now if we apply first law to the air in cylinder B, so what we get is delta U is Q minus W. Since cylinder B is insulated, so there cannot be any heat transfer. So heat transfer Q is 0. So whatever change in internal energy is there is equal to the work which is done on the system. So WB is mCV T2 minus T1. So WB is minus 0.15 into CV is 721.7 for air, and 327 minus 300, so which is the initial and final temperature. So that gives you WB is minus 2.923 kilojoules. So using this and since we know the final pressure in cylinder B, so we're using the same expression using the force balance which we did, so that will still remain the same. So now instead of the pressure in cylinder A, we know pressure in cylinder B, so we can estimate the other. So substituting the values again, this is how the expression will look. So substituting the values, we get P2A as 258.7 kilopascal. So now for finding out temperature in A, we know the pressure, we know pressure, we know the mass, so only unknown is the volume. So volume can be calculated, so initial volume plus the change in volume, which is 2 into area of piston A, so that gives you 0.10212 meter cube for the final volume in cylinder A. So now we know all the values, we can substitute it in a ideal gas equation to find out the temperature. So P2 into V2 divided by MAR. So P2 is, we have found out 258.7 kilopascal into 10 power 3 converted into pascal into 0.10212 meter cube divided by mass is 0.2 and R is 288.68. So that gives you a temperature is 458 Kelvin. So next is we need to find out how much heat has been supplied. So for that so delta U is Q minus W. So we know the initial and final temperature, and we know the work done by A can be calculated based on W system plus W surrounding 0. So the sum of all works. So the only work which we don't know is the work done by cylinder A. The rest we have all calculated. So delta Q is delta U minus WB plus W piston plus W atmosphere. So that gives you the work done by A, and using with delta U you can find out the heat. Delta U is mCV delta T, and since the temperature, we know the temperature T2A is 458 and we know the initial, using that substituting the values we get the net work and the delta U, substituting we get Q as 26.714 kilojoule. So that is the heat which is supplied to cylinder A to do this process. Any doubt in this problem? So there are a lot of parts which was interlinked to other. I'll just run through. There was a lot of parameter which we have to find out. I'll just run through again what was done. So we had two cylinders which are connected by a common piston, and each the piston area is different. So these are the values which we need to find out. So initial pressure, volume and temperature for cylinder A is given, and the volume and temperature in cylinder B is given, and by adding heat in cylinder A, the piston is moving downwards by 2 meter. So that is the case. So since we know pressure, volume and temperature, using ideal gas law, we estimated what is the mass in cylinder A. So that finishes the first one, and then we need to find out the initial pressure in cylinder B. So to do that, what we did is we did a force balance across the piston. So we calculated the net pressure on the top face and similarly the bottom face and the weight of the piston. So we balanced that. So that gives you an expression with pressure A, cylinder A, pressure in cylinder B, and the atmospheric pressure and the weight of the piston with the areas and so on. So that gave an expression. So using that, now the only unknown was the pressure in cylinder B. So we estimated the pressure. So the second part is done. So now since we initially knew the volume and temperature, so with this pressure we estimated using the ideal gas law what is the mass in cylinder B. So the mass of gas in cylinder B. So that gives you the mass, the third C part. Next is the atmospheric work done by the atmosphere. So the atmospheric work is P delta V. So we calculated what is the change in volume for A and change in volume of B. So the only thing which you need to be careful here is how the work is being done and what you are considering the system. So when you are taking the atmosphere, your atmosphere is your system. So there A is doing work on the system, so you get that is negative, and B, your the atmosphere is doing work on B, so that is positive. So you need to be careful on sign there. So P delta V, that will give you the atmospheric work, and then piston work is the change in potential energy. So mg into delta H, which is 2 meter, which is negative minus H, and then final volume in B. To find out final volume, we just did initial volume minus the volume displaced, that is area into the length which the piston displaced down. So that gives you final volume in B, and similarly you can find out the final volume in cylinder A. So next is final temperature in B. So final temperature, we knew to do an ideal gas equation, we knew pressure, the final pressure is given, we know the volume which we calculated, and we know the mass which we calculated previously, so we can find out temperature. And similarly the final temperature in A, so we know the volume, we can calculate volume plus the volume displaced, and then we need to find out the pressure. So the final pressure in B is known, so applying the same force balance, we can find out the pressure in B A, so that gives you the pressure. Then we know the mass, so we can calculate the temperature. So that finishes the J part. Then the last part is heat supply. So before finding out heat supply, we also need to find out the work done by B. So for doing finding out the work done by B, we don't know what the process is happening inside the cylinder B. So what we do is we apply an first law for the cylinder B, because that depends only on the first and second state, because this is insulated, Q is 0. So what you get is delta U equals W. So delta U depends only on the initial and final states. So we know the initial and final state, so mCV delta T, you get the work. So work in cylinder B is known. So using this, you similarly apply the first law for cylinder A, and work in A can be found out using W system plus W surrounding. So you can find out WA, and delta U for the cylinder A is also known, because you know temperature initial and final. So you can find out mCV delta T. So that will give you the heat which is supplied to cylinder A. that's the run through of that question. I hope this is clear. So moving on, the next question. It's a simple question. MCQ: in a free expansion process, choose a statement for heat and work transfer. So what do you think is the correct option? Option A, the total work done is 0. B, the total heat transfer is 0. C, work done is 0 but heat increases. D, both statements A and B. So answer is option D, both A and B are 0. Sorry, both work and heat transfer will be 0. Because it's an unrestricted expansion, there is no work which is being done by that, because as I told in the previous class, there is no restriction for this, so it's not doing any work, and because of that also there is no heat transfer. The simple problem on first law. So you have a hot summer day, you turn on a fan and leave in the morning, but close the room. So when you return, what will be the room's temperature? So assume it is insulated room, so there is no heat transfer. So you have fan running, you switch on the fan, you forget, but the room is insulated, and so when you come back, what do you think the room temperature will be? Will it be cooler because the fan is running, or warmer, or do you think there will be no change, or it cannot be predicted? So what do you think will be the case? It's a simple question, but gives you a good understanding on the first law of the equation. How do you apply that? That's the hint. Take a guess. Okay, so in this case what will happen is, so you consider this room as your system now. So you apply a first law for this. So from the point where when you leave the room and when you come back, those are the two state points to consider. So initially you have some temperature, and then when you come back it is at some temperature. So till that point there is no heat transfer which is happening, so your Q is 0, but you are supplying electrical energy. So that is kind of a form of work which you are doing. So the work is being supplied to the system, and because of which the fan is running. So you are doing work on the system. So the work is being supplied to the room. So there is work in input. So you have Q minus W. Here W is negative anyway, so that becomes positive. So your delta Q is 0. So it becomes delta U is W. So in this case, the change in internal energy of the system, in this case the air in the room, is positive. So since delta U is mCV delta T, your dt is positive. So there will be a temperature rise. So it will be warmer when you come back. So the answer is option B. Some problem here. So the answer is option B. It will be warmer. So the second case is instead of your fan, you have your fridge which is open. So what do you think will happen in this case? Same case, instead of fan now you have fridge or a refrigerator which is open, which is you have left the door open. So what will happen in this case? The temperature of the room will gradually increase, no effect on room temperature. The temperature of the room will be decreased to refrigerator temperature, any of the above depending upon the refrigerator type. So what do you think will happen in this case? Think over it. Try to apply the same first law. So here there should be no change. This will be same as the previous one. The room will get hotter. Why? The same what I explained in the previous case. You have work which is coming in, there is no Q which is going out. So your delta U will be positive and the temperature rise will be positive. So that's T is greater, so it will be warmer. So you're just having fridge open, it's misleading. So when you see go to second laws and so on, there will where you will find out about a refrigerator and heat pumps and so on. So there you will find that even though Q which provides cooling, it will also reject heat. So that will be greater. That will be equal to the what work you are providing. So essentially in this case, it is like whatever work you are providing, that is went into heating. So the same case. So here also the temperature of the room will gradually increase. So next question. A closed system evolves from an initial state 1 to a state 2 along the path x. It then comes back to state 1 following two different paths y or z. During this process, the system transfers work and heat energy with its surrounding. So initially path 1 to 2, so this is how it's going, and then it's coming back from path 2 to 1 or the next one by xy and then or xz. So that's the process. So in this case you need to find out the system what is the work and heat energy. So again first law, so 1 to 2, 2 to 1, so it forms a cycle. Two processes is forming a cycle. So you have to find out the heat and work. Please try this. I'll give you a couple of minutes. It's a straight away easy problem. So in this case, since this forms a closed cycle, if you apply the first law, what you will get is the delta U 0. So Q net is W net. So for the first case, 1 to 2 to x y, so you have minus 10, then plus 7, so that gives you minus 3, which will be equals to whatever W here in 1 to 2 plus 4. So if you take it the other side, what you get is minus 3 minus 4, which is minus 7. So minus 7, and similarly 1 to 2 and 2 to 1, x and z. So minus 10 plus some x, and then W is minus 7. So minus 7 plus 8, what you get is 1. So here whatever Q at Z is 11. So that's how it is satisfied. So that is 11. Similarly, for second case, the first one is some x plus 4 is equals to minus 7 plus 9. So you get 2. So here it's minus 2. The first one for Q for x is minus 2. And then similarly, so 2 minus 10, which is minus 8, which is Q is minus 2, which we found out, plus minus 10 for Z. So you get minus 8. And similarly, W is minus 7 plus some x. So we get minus 8 on the left hand side and minus 7 plus x on the right hand side. So what we get is minus 1. We have minus 8. This is, I think there is a mistake here. Actually, minus 1. So moving on to next question. A spherical balloon has a diameter d1 when the pressure of the gas inside is P1 and the atmospheric pressure is P0. A process now occurs in which the balloon diameter increases to d2 and the pressure of the gas is proportional to the balloon diameter. So derive expression for the work done by the gas and the work done on the atmosphere. So what we have is atmospheric pressure is P0, and initially the balloon is at diameter d1, which is with pressure P1, and they say when it is rising, it pressure increases proportional to the diameter. So we can assume P is any linear function of diameter. So we can assume P is A times diameter plus B. So we have two unknowns. So we need two conditions. So initially when the diameter is 0, which is atmospheric pressure, so there should be no pressure. So it will be pressure P0. We know that one. The second condition is given P, which is diameter d1 at pressure P1. So substituting that, we can find the expression for the pressure in terms of P0 and P1 and D0 and D1. So that's a straight line equation here. And then using that, now what they say is derive expression for the work done by the gas and the work done on the atmosphere. So when you are filling the balloon, so the balloon expands and it goes to diameter d2 from d1. So what is the work done in this case? So this is how it looks. So P is A times D plus B. So at P0, P is P0, your diameter is D0, and when P is P1, your diameter is D1. So B is P0 and A is P1 minus P0 by D1. So that's the expression which you get. So now the work done by gas is simple, integral P dV. So substituting the pressure equation here, we get this is the equation, and volume you can write it as 4 by 3 pi r cube. So we convert into diameter, and then differentiate with respect to volume, what you end up with is 3 pi d square into d times d, so the derivative of diameter. So integrating this, you get p1 minus p naught by d1 into pi by 8 into d square raised to the 4 minus d1 raised to the 4. So this is the work done by the gas, and then work done by the atmosphere is nothing but the change in the volume times pressure P naught. So here if you see, these two are not equal. Ideally the system plus surrounding us should be 0, right? So whatever the gas is doing in the atmosphere, so in this case what is happening is the difference is what is being will be done to stretch the balloon material. So that's where the other force which will go. So the difference is equal to the work done to stretch the balloon. So in this case we found out P, we substituted P and integrated it. So we got work done by gas, and we found out P naught delta V to find out work done by atmosphere. So any question in this? So next question. A DC electrical motor is used to operate the hoist mechanism in a crane. The motor is supplied with 150 volts and 10 amps from a DC source for a period of 2 minutes. The torque provided by the motor to the hoist shaft is 230 Newton per meter at 660 rpm. The hoist mechanism lifts a mass of 3 tons through a height of 5 meter. Calculate the work interaction for the DC source, motor, hoist and the mass. So you have a DC source which is a battery, so that is supplying energy to the motor, and then motor is driven by driving a hoist, and then hoist is lifting mass. So that is the case, and you have to do work interaction for each of these components. Try solving this. You take each of the component, you find out what is the work interaction in each of the component, whether which is work which is receiving or it's delivering, what is happening. So what we have is each 4 components. So one is DC source. So whatever there is nothing which is coming in as work, only DC power source is driving, so it is delivering work or it is providing work. So that is equals to the electric which is done by the uh, source. So this is how it looks. So you have source, you have motor, and then a hoist which is running at 60 rpm, and then which is raising a mass. So initially when you consider source, so DC source that is providing work, so that is the only work which is happening in the source. So if you consider apply this control volume across source, so there is a work which is coming out, and that work is equals to 150 into 10 multiplied by 2 into 2 minutes for period of 2 minutes. So that comes out to be 180 kilojoules. So we have 180 kilojoules of work which is delivered by the battery, and then this work is going inside the motor. If you consider the motor, so motor is having 2 parts. So it is receiving work from the battery, it is coming in at 180 kilojoules, and then it is doing work, and that work is given by your torque into omega into T. So your torque is 230 Newton meter, and omega is 2 pi n by 60. So n is 60 rpm. So 2 pi into 60 by 60 into it is for 2 minutes, so 120. So that gives you 173.42 kilojoule. So what is happening, this difference? So that is due to the friction and the other losses. You have reduced work. So that is the net work consumption. Will be net work consumption is 180 minus so minus 180 because you are doing in work plus work delivered, which is 173.42, gives you minus 6.58 kilojoule. So that is the net work consumed by the motor. So this is to overcome your friction and other losses. And then comes the hoist. So in case of hoist, hoist is W out minus W in. So W out is minus 173.42 and W in is mgh. So what you get is net is minus 26.17 kilojoule. So that is the work we dissipated in the hoist. And then mass. So mass is the change in potential energy. So you get W mass is minus mgh. So it is minus 147.15 kilojoule. So that is the work which is received by the mass to raise its potential energy. So next question. Air is contained in a piston cylinder assembly initially at a pressure of 5 bar and 300 Kelvin. A paddle wheel fan within the cylinder is rotated using an electrical motor till a work of 75 kilojoule per kg of work is done on the air. So the wall of the piston cylinder assembly are cooled using cold water such that the temperature of the air does not rise due to the pedal work. However, the piston is allowed to expand so that the volume occupied by air, initial air, is doubled. Determine the amount of heat rejected to cold water. So you have all three happening. You are supplying work, and because of which your air is getting heated, it is receiving energy. So you are cooling it such that the temperature remains constant. So your temperature is remaining constant throughout. So you are receiving work and it is doing some work, and there is some heat which is getting rejected. So that's the case. So you have a cylinder piston cylinder assembly initially. So within the cylinder you have a paddle wheel or a steerer wheel. So it is supplying work to the air inside. So that is a work in, and then because of which the temperature will rise because it is receiving work. So that is reduced by doing work and rejecting heat, such that your work your temperature remains constant. So we need to find out how much work does the piston do and how much heat is rejected. So how will we solve this? So first, since the temperature is not rising, your delta U is 0. So now if you apply the first law for the system, what you will get is your net Q is equals to delta U plus W, net W, since delta U is 0, and W net is the W gas, and which is the work done minus the paddle work, and the gas is integral P dV. Since the temperature is constant, so we can assume for ideal gas is RT by V. So integrating we get RT ln V2 by V1. So this is the work done by gas. So substituting the values, R is 287 for air into 300 into ln, because the volume is getting doubled, so V2 by V1 is 2. So this gives you 59.7 kilojoules. So that is the work done by the gas, and the net work which it receives is 75 kilojoules. So minus 75. So this gives you Q12 is minus 15.3, which is rejected. I think two more problems. So the following table gives data in kilojoule for a system undergoing a thermodynamic cycle. Determine the missing table entries and whether the cycle is work producing or absorbing. So these are the four processes through which a thermodynamic cycle is going through. So we need to find out the missing entries. So just like previous one. So how will you do this? So first we cannot do, we'll consider each of the process first, because you can apply first law for each of the processes. So first one, there are two unknowns, so we cannot find. So we'll go to process 2 to 3 first. So we have delta U, the only unknown is Q, we know W, so we can find out Q. So delta U is Q minus W. So we get 670 minus 230, so we get 440, so that is Q. And then for 3 to 4, again there is two known and one unknown, so delta U. So delta U is Q minus W, so delta U will be minus 920 in this case. And similarly for 4 1, Q is unknown, so again delta U is Q minus W. So since W is 0, Q is minus 360, so we know all three. So now the only unknown is 1 to 2. So since this goes through a cycle, we also know that for process all the process summed, we will get Q net is equals to W net. So we add up all Q and add up all W, we can find out Q for process 1 to 2, and again applying first law we can find out delta U. So this is how it looks. So as I said previously, for process 1 to 2, delta U is Q minus W. So we get Q as 900, and then process 4 to 1 is Q minus 360, and process 3 to 4 minus 920. So we'll add up all Q and W. We get W net is 540, we get Q is 0 for the first case. So delta U will be again similarly the net delta U is 0. In this case it will get delta U1 is 610 kilojoule, or you can apply first law for the first case. So both you can do. And since W net here, if you add up all, that you get W net, that is positive. So the cycle is work producing, so you will get receive work, so hence positive. So next case is a steady state operation. A gearbox receives 60 kilowatt through the input shaft and delivers power through the output shaft for the gearbox as system. The rate of energy transfer by convection is given by Q is minus HA TB minus TF, where H is given and area is given and the TB is given and TF is also given. TF is the surrounding air. So for the gearbox, I evaluate the heat transfer rate and the power it delivered through the output shaft. So again, you can estimate Q. So all the values are known. So that comes out to be minus 1.2 kilowatt. So that is the heat transfer which is happening, and since it's negative, so it is rejecting heat. So applying first law, assuming that there is no temperature change, so the delta U for the system is 0. So Q minus W is 0. So our net Q is net W. So the work which is coming in plus work which is going out is equals to the heat transfer. So W2 becomes Q minus W1. So minus 1.2 minus of minus 60, which comes out to be 58.8 kilowatt. So that is the work which is delivered. So here it minus 60 because that is the work which is supplied, and 58.8 is which is delivered. That's why it's positive. So with that, I finished the questions which I have prepared for today. If you have any questions, you can ask. So next week we also look at some more problems in with first law and also with mixtures and two phase. Okay, if there is no doubt, we can end the session for today. Thanks for joining, and see you next week. Same Tuesday, 6 o'clock. Thank you.